Alright, so Le Chatelier's principle states that when a reversible process, when a reversible process is disturbed, after reaching equilibrium, then it will proceed in the direction that will best relieve the stress caused by that disturbance. That's basically what Le Chatelier's principle states. It's dealing with 3 individual conditions, but it's basically stating that if you have a reversible process, so a chemical reaction that is reversible, say, like if I had, this is one we do a lot, but if we take the formation of ammonia as an example, it's a reversible process, and if we were to put hydrogen gas and nitrogen gas inside of a container and let that reaction just run, eventually it'll reach equilibrium. So you'll have an equal amount of NH3 converting back into gases as you would having these gases convert back into ammonia. Alright. But if you disturb this reaction, for instance, you maybe change the pressure, you change the temperature, you add a certain gas to one of the two, either the reactants or the products, then that introduces a disturbance. One of the 3 disturbances that we're going to talk about are a concentration change. So a concentration change. Alright. So you can have either the products, and then remember that these brackets indicate concentration, so you can have the concentration of the products go up, or the concentration of the products can decrease, so it can go down, or you can have a condition where the concentration of the reactants is increasing, or it's going down. Alright, so in this first situation here, I'm going to use H2 as our, I'm going to use actually the same exact reaction as kind of our example here. Let's just say for a minute that we have 3 H2 gas plus 1 mole of nitrogen gas, and it's in a equilibrium reversible reaction with ammonia, which it forms. Does that. Alright, so if we do this, and let's just say for a second that we increase the concentration of the products. So if we increase the concentration of our products, remember that this are our products, right? The ammonia as products, and the reactants are here. The reactants. Alright. So if we increase the concentration of these products, otherwise we add ammonia, what will happen is that the concentration of NH3 will increase, and then what's going to be forced to happen is the excess ammonia will start to convert into more of the reactants of the hydrogen and the nitrogen. So as you add more NH3, it will actually cause the equilibrium to shift to the left. Okay, so if you increase the products, okay, then you have a shift left. And then you have the concentration of the reactants will also increase. Okay, and the reason being is because if you had, say, I don't know, 0.005 moles of hydrogen and the same for nitrogen, and you had, let's see, 0.005 for NH3, and then you increase NH3 to, say, like 0.010, like you doubled it, what's going to end up happening is some of the 0.005 will actually leave. That excess will leave and start to also be converted and split with nitrogen until eventually equilibrium is reached between both the reactants and the products again. It's a lot like a wave. If you can picture a wave where it's like, if this is the wall and you have a lot of water here, right? And this is another area of the pool over here. And what's going to happen is this water is going to travel in this direction to make everything even. And it's kind of the same thing that's happening here in equilibrium. When you have equilibrium, you have the rates of the forward and reverse are the same, but if you have more product, what actually happens is the rate might actually increase slightly going left because you have more product, so that therefore you can convert more of that product into reactants, the opposite of the forward reaction, the reverse reaction. All right, so let me erase that real quick. Okay. All right, the other condition is maybe you want to decrease the products. Okay, so let's just see what that would look like. Okay, I'm going to use purple for this. Okay, so if you put this down, okay, so if if we are decreasing ammonia, okay, so if we remove ammonia, okay, if we remove ammonia, then the concentration of NH3 is going to go down, okay. If the concentration of NH3 is going down, what that means is that in order to get back into equilibrium, we're going to have a shift to the right. Okay, the equilibrium will shift to the right, and the concentration of the reactants is also going to decrease. Okay, so it's an overall decrease. So you're going to have the reaction shift to the right, because what's going to happen is if this goes down, right, so if it goes down, there's less of NH3, and so you get more of this nitrogen and hydrogen converting back into NH3, so that we're going to get back to equilibrium. It's like there's too much on this side for equilibrium to, or you basically disturb equilibrium. Therefore, these things on this side are going to convert together and try to even things out. So they're going to shift, and more NH3 is going to be formed on this right side. So you remove ammonia, the concentration of NH3 goes down, and then the reactants, the concentration will also go down, because as these are converting into ammonia, their concentrations are decreasing because there is less available. Okay, so let's do the opposite of that. All right, so if you increase the concentration of reactants, so if I increase the concentration of hydrogen, or if I increase the concentration of nitrogen, okay, so I increase both of those, what's going to happen is you're going to have a shift to the right. Okay, so equilibrium is going to shift to the right. Okay, so if you increase concentration of H2 and or the concentration of N2, okay, that's what's going to happen. You increase that, you're adding hydrogen. Okay, so add hydrogen or nitrogen. Okay, and that's what's going to happen. You're going to have an increase because what's going to happen is you're going to have too much reactants and products. It'll disturb it, and then it'll force the production of more product. Okay, so you're going to have a shift to the right. The concentration of the products then is going to also increase. Okay, products are going to increase because the more hydrogen and nitrogen you have, the more ammonia that you're able to make. All right. And finally, let's do this second option here is that we remove hydrogen or nitrogen, either one. Okay, so if you remove hydrogen or nitrogen, that means that you are decreasing the concentration of hydrogen or decreasing the concentration of nitrogen. And you're doing the same up here to make sure we stay consistent. Okay. But you're decreasing both. What's going to happen is there's actually going to be an equilibrium shift to the left. Okay, so we're going to have a shift to the left. Okay, a shift left, and the concentration of the reactants, or I'm sorry, of the, we're actually talking about products now, aren't we? Okay, I'm sorry, the concentration of the products is also going to decrease as well. All right, okay, so the reason being is because when you decrease the amount of hydrogen and nitrogen, now in order to reach equilibrium again, it's been thrown off, so to reach it again, more ammonia is going to have to convert into hydrogen and nitrogen to get back to equilibrium. It's seeking equilibrium. Okay, so more ammonia will switch and turn into nitrogen and hydrogen. All right. Something to remember about this is that KEQ for all of these situations, okay, it does not change. All right. Does not change. Remember that the equilibrium constant, KEQ, is a measure of the rates of the forward and reverse reaction. The rates are basically going to stay the same, but what we're really looking at is how does Le Chatelier's principle account for the change in concentration of both the products and the reactants if you disturb the reaction by changing one of the concentrations of either the products or reactants. So why do the reactants concentration change if I change the concentration of the products or vice versa? Okay, so here KEQ is not changing because the rate itself, there's not really anything changing about the rate. Okay, so I'm sorry, so I'm going to restate what I said about KEQ, but actually what I mean to say is that KEQ is not going to change because remember that KEQ is the constant. Okay, so it's the constant at equilibrium, right? And so once equilibrium is again reached, when you disturb it, the rate will change actually initially. If you have more NH3, it'll actually force its way across into the reactants quicker than whether the nitrogen, the hydrogen actually becomes NH3. Okay, so the rate will increase initially, but then once it reaches equilibrium, it'll be the same. So once equilibrium is again reached, the constant is going to be the same. Okay, because at equilibrium, okay, so at equilibrium, the rates will be the same. All right. So that's all I have to really say about concentration change. All right, so the next thing that could be considered a disturbance is a change in pressure. Change in pressure. Okay, and remember that that is where you might have an increase. Okay, so you can have an increase in pressure, or you may have a decrease in pressure. So for an increase of pressure, what you need to remember is if you increase the pressure, that means that equilibrium shifts to the side with fewer moles of gas. Okay, and then if you decrease the pressure, the opposite is true. So if you decrease the pressure, equilibrium shifts to the side with more moles of gas. All right, so a decrease in pressure, it'll shift to the side with more. If you increase the pressure, it'll shift to the side with fewer. Okay, and that is because the external pressure will force, if you have a lot of moles of gas on one side of the equation or in one state, they will try to make themselves more compact. So if you have 4 moles of gas on the left, as if, right here we have 4 moles of gas on the left side of this equation, and we got 2 moles of gas on the right side here. If you increase the pressure, it'll force these guys to kind of convert quicker into ammonia, because there is kind of not really the space. They can actually conserve space if there's actually fewer particles. So while they are nitrogen and hydrogen, there's a lot more particles of gas. But then once you increase the pressure, they're trying to relieve that pressure. And so the best way to relieve it is to be condensed and become ammonia. And you might remember this picture where we have 3 moles of hydrogen on the left, okay, and a mole of nitrogen, and then 2 moles of NH3. So it actually conserves space. If you were to take all the space that gas takes up at STP, so at standard temperature and pressure, you'd have 4 moles. It would take up approximately, what's that number? 89.6-ish liters, about 90 liters of space. Whereas if they convert into ammonia, they only take up approximately 44.8 liters of space. So like here you have like 22.4 times 3, right? Plus 22.4, and then here you have just 22.4 times 2, if you're keeping temperature the same, okay? So it actually conserves space, all right? But if you decrease the pressure, the opposite will happen. They'll want to spread out, okay? They want to diffuse. If the pressure is decreasing, the gas will not want to stay next to each other. It'll want to spread out more. So actually, you're going to have a shift towards the left, to the side that has more moles of gas. Okay, if you have a decrease in pressure. Now this situation is not always going to be true, and there's going to be a couple that you're going to see as kind of exceptions. But if you have something like H2 gas and you mix that with iodine gas, so hydrogen and iodine, and you mix those two together, you end up with 2HI, so 2 hydrogen iodide, if this is a gas. And if I increase the pressure, what's going to happen? Okay, so if I increase the pressure, or if I decrease the pressure, well, you'd be like, it's going to shift to the side with fewer moles of gas. Well, which side is that? This side has 2. This side has 2. So therefore, these actual changes in pressure are not going to do anything to disturb equilibrium. Okay, so equilibrium is only going to be disturbed, really, if we have a different number of moles of gas on one side of the reaction versus another. What if I did this one right here? If I did 2 2SO3 gas, so sulfur trioxide, and I divide those into kind of the component elements here. So okay, if I decrease the pressure, okay, so if I decrease the pressure, I'm sorry, there's 3 on this side and 2 on this side. Okay, so if I decrease the pressure, it'll force the gas to go in this direction. Okay, so this is decreasing pressure. But if I increase the pressure, it will be forced in the opposite direction. Okay, it'll go from 3 to 2. Okay, 2 moles of gas. Okay, all right, and this also, this 4 to 2, this is for an increase in pressure. Okay, so increase the pressure, and it shifts to the side with fewer moles of gas. You decrease the pressure, it shifts to the side with fewer moles of gas. I'm sorry, more moles of gas. Increase the pressure, goes to fewer moles of gas. All right, and the last one is a change in temperature. So if you change the temperature of a gas, this is number 3, temperature. Okay. So increasing the temperature of a gas. Well, there's different things that we can do here. If I write out the equation for sulfur dioxide, 2SO2 as a gas plus oxygen gas makes sulfur trioxide, and there's 2 of them, and that's also a gas. Well, what you need to know about the formation of sulfur trioxide is that it also produces heat. All right, heat is produced. Because heat is produced, this reaction is exothermic. Okay, so exothermic heat is a product. Okay, exothermic heat is a product. So with temperature increases, there are 2 types of reactions. There's an endothermic and exothermic reactions, and then if you decrease the heat for an exothermic reaction or increase it, or for an exothermic reaction, do you decrease it or increase it? So we have 4 situations. We have increase heat, exothermic. Okay. We have decrease heat, exothermic. We have increase heat, endothermic. And we have decrease heat, endothermic. All right, so those are our 4 situations. So if you increase the heat of an exothermic reaction, and this reaction right here is actually going to be our exothermic reaction. Okay, so heat is a product. I'm going to take this boy and move him up here. Exothermic heat is a product. So if you increase heat, okay, so if you increase the heat, it's basically going to kind of act like, its own product with a concentration. And what happens when we increase the concentration of a product at equilibrium? If you guessed, it shifts to the left, then you are correct. Okay, so what's going to happen is more of the reactants are going to form if we increase the heat. All right, so we increase the heat, more reactants form. Okay, so we have a shift left, and more reactant forms. Okay, and then what if we decrease the heat? So let's just say that we were to decrease the heat. Hopefully you can see this yellow. But if we decrease the heat, what happens? We get a shift to the right. Okay, shifts right. So shift right, more product forms. And this is actually a technique that is used often to make a reaction proceed faster. If you know that the reaction is exothermic and it creates heat, if you put the reacting vessel, whatever it's in, into an ice bath, that'll take a lot of the heat out. And as heat is taken out, the idea is that more of the reactants will try to form products and release that heat. And so that's kind of a lab technique that they use to make sure that we can not reach equilibrium too quickly, and that we have more products than reactants at the end of the day. Okay. On the other hand, we have an endothermic reaction. Okay, so I'm going to put endothermic. Okay, and there's lots of opposites here. So you can guess if exothermic is where heat is a product, you can guess endothermic is that heat is the reactant. Okay, or a reactant. And a endothermic reaction is the formation of hydrogen iodide, okay, which we've talked about. Gas plus heat is in a reversible reaction with hydrogen iodide as a gas. All right. So if heat is a reactant for an endothermic reaction, then what happens when we increase the heat? Okay, so we increase the heat. Well, if we increase the heat, remember the heat, it's going to act like a product with a concentration, so it's going to push the equilibrium to the right. Okay, so it's going to have a shift right, okay, and more product forms. Okay, and then the opposite is true if we decrease. If we decrease the heat, okay, you decrease the heat, then you're going to have a shift to the left. Okay, so you'll have a shift left, and more reactants will form. All right. So that's the effect of heat. Now, when you do this and you remove heat or increase heat, you actually are going to change the equilibrium constants. Okay, so KEQ is actually going to decrease. Okay, so KEQ, I'm gonna just write it as KEQ goes down. Okay, because if more reactants form, that means that there are less products. And remember that KEQ is products over reactants. So if you remove product, then of course your KEQ is going to decrease. For the exothermic reaction, if you decrease the heat, KEQ will also increase because more products will form there. For an endothermic reaction, KEQ is actually going to increase for an endothermic reaction. Okay, so KEQ is going to increase there, and then if you decrease the heat, KEQ will also decrease in an endothermic reaction. Okay, so that is it for temperature. The final one is a catalyst. Okay, the effect of catalysts. And if you don't know what a catalyst is something that speeds up a reaction without being consumed, both the forward and reverse reactions. So know that when you're in equilibrium and you have both a forward reaction and a reverse reaction, the reactants are forming products and the products are forming reactants. So the catalyst basically speeds up both of those reactions but is not consumed in the reaction. It's not actually used up in the reaction. But it helps the reaction achieve equilibrium faster than it would on its own. Okay, so if you use a catalyst, nothing really changes about this. There is no shift. Okay, you add a catalyst. There's no shift in either direction because what a catalyst does is both the forward and the reverse reaction. So you're not going to have a particular shift. You're not going to have more products form. Okay, so no more of each product or reactant. Okay. Okay, so you're not going to have more of a product or reactant because it's not really adding to the concentration. It's just making the thing go faster. And then, of course, KEQ is going to be the same. Okay. It doesn't change, and that makes sense because the rates are not changing, or the rates in proportion to one another are changed. So, KEQ is the rate of the forward and the reverse on top of one another, and if both of these increase by the same amount, then there is no change to the overall KEQ. Like, they're both going to be the exact same. All right, so that is it for Le Chatelier's principle. We are going to move on from here to start talking about acids and base. Acid-base chemistry will be our next thing. All right, so here are some application problems for Le Chatelier's principle, and we'll also dip into some chemical equilibrium problems. All of these are kind of interconnected. So, page 404 of the textbook talks about some application problems for equilibrium in this chapter, and it wants us to write the equilibrium constant for this reaction. Okay, so it wants us to write the equilibrium constant for each reaction. Here, we're going to start with A, and then because we have something else that we can do with this. So laughing gas can decompose into nitrogen and oxygen. So dinitrogen oxide is also known as laughing gas, and here's the decomposition reaction for it turning into nitrogen and oxygen. And you can see we have this arrow here, so it's an equilibrium arrow. And so it does go into equilibrium. So what is the equilibrium constant? So remember, KEQ is equal to the concentration of the products coefficient as a exponent divided by the concentration of the reactants with their coefficients as their exponents. Okay, so for this one itself, our products are N2 and O2. Okay, so we have concentration of N2, and we have a coefficient of 2 on there, and that comes from just this right here. And then we multiply that by the concentration of oxygen, or O2, and that whole thing is going to be divided by the concentration of N2O with a 2 as its exponent. Okay, so that is going to be KEQ right there. Okay, so next we have carbon monoxide reacting with hydrogen gas to make methane and water. What is the equilibrium constant for this reaction? Okay, so we're going to use the same formula above, and we will say that our reactants are CO and H2. Those are going to be in our denominator. Let's write our numerator first. Our products are methane. Okay, so we have the concentration of methane. There is no coefficient, so it does not have an exponent. And then we have water, so that is the second factor in our product here. Okay, so products are always over reactants. That's our numerator. And then our denominator is CO, carbon monoxide, without an exponent because it does not have a coefficient. And then hydrogen gas with an exponent of 3. That is our KEQ for that reaction. All right, our next one is carbon monoxide reacts with hydrogen gas to make what is called methanol. What is the KEQ for this reaction? Okay, so KEQ, using the same formula as above. Our products are methanol, and we do see that it is a gas, so it's okay for us to write that up here as a gas. And then our reactants are carbon monoxide, no exponent, and hydrogen gas, again with an exponent of 2. All right, so that is KEQ. Okay, so the next thing is that we need to predict the effect on equilibrium if you increase the pressure on each of these reactions. All right, so in reaction A, with laughing gas, if you increase the pressure, you know that the equilibrium will shift in the direction of either the product or reactant that has the fewest number of moles. Okay, so we see that in this first reaction, we have 2 moles of gas on the left side and 3 moles of gas on the right side. So if we increase the concentration, or sorry, the pressure, it'll force equilibrium to the left. Okay, so if you increase pressure, shift left. Right here. Okay, next, in B, we're going to do the same thing. You see on the left here we have 4 moles of gas on the left side, and we have 2 moles of gas on the left side, or the right side. So if we increase the pressure, okay, so increase pressure, you're going to get a shift to the right. Shift to the right. Okay, and then the final one, pretty plain to see, we have 3 here, and we have 1 over here. So again, we increase the pressure, okay, shift to the right. Okay, so that's how you're going to predict the shifting of equilibrium based off of the moles of gas in the problem. Alright, so we have a different problem from the book. This is coming from the still page 404, but it's going to be similar to the homework problems that I've assigned when it comes to these. Okay, so we have N2 gas combining with hydrogen gas to make ammonia. This is a trusty problem that you're going to see a lot. And the scientist seeks to determine an equilibrium constant at 450 degrees Celsius. Okay, so after permitting a mixture of nitrogen and hydrogen to react and reach equilibrium, he found that nitrogen gas, the concentration of it is 1. Hydrogen gas, the concentration was 0.0769, and for ammonia it was 0.000200. So we want to calculate KEQ at this temperature. Alright, so I'm just going to use the same formula here that we have for KEQ. Remember that KEQ is equal to concentration of the products over reactants, and we always use gas and aqueous. We never use liquids or solids. So for this particular reaction, our product is ammonia, so we're going to use NH3, and the exponent here is going to be a 2. Okay, so that comes from right here. Okay, that 2 right here we're going to use as our exponent, and then for our denominator we're going to put nitrogen gas there. There is no exponent because there is no coefficient, and then for hydrogen we're going to put H2 there, and 3 is going to be our exponent. And then with this, we're going to go ahead and plug these values in for our concentrations, because we found each of these concentrations to be like so. Okay, so we want to calculate KEQ at this particular temperature. So here we go. So for NH3, we had 0.000200. Okay, so I'll just put all those in there, make sure I don't miss any zeros here. Okay, and we're going to square that, right? Okay, and then in the denominator we have 1. All right, and then we're going to multiply that by whatever hydrogen is, which is 0.0769 cubed. All right, and I'm going to put that number, whatever that number is, I'm going to put its result down below. Okay, so you just have to plug this into your calculator correctly, and that's all. And then the final result is 0.0000, so there's 4 zeros, 87959 is what I get in my calculator. So if we wanted to simplify this, this would be 8 this would be like 8.8 times 10 to the 10 to the minus 5th power. Okay, so KEQ equals 8.8 times 10 to the minus 5th power. Alright, so that's good for the first part, but let's look at the second part. So the second part says that the scientist repeats the same exact experiment under the same conditions with different amounts of gas in the reaction vessel. The scientist finds that the concentration of hydrogen gas is 0.0375 and the concentration of ammonia is 0.0002. 0.00318. Use the value of KEQ already determined to calculate N2. Okay, well, it tells us right there we're going to use the value of KEQ that we already determined, and then we're going to also use this this equation right here to help us solve for KEQ. So what we're going to try to find is N2. It already tells us what we're trying to solve for. It gives us KEQ from this problem right here, NH3 and H2, so we can solve for N2. Right, so let's do that. So again, KEQ is equal to NH3 squared divided by nitrogen, hydrogen cubed, and then that equals 8.8 times 10 to the negative 5. All right, let's remember that. Okay, the first thing I want to do though is what I can do is divide both sides by KEQ. Okay, so if I divide both sides by KEQ, I'm left with 1 equals NH3 squared divided by N2 H2 cubed times KEQ. And then what I'm going to do with that, I'm going to multiply both sides by N2, or the concentration of N2. Do that, multiply both sides by the concentration of N2. Do that. And you get that the concentration of N2 is going to be equal to concentration of NH3 squared divided by the concentration of H squared, or I'm sorry, of hydrogen gas to the third times KEQ. Alright, let's put this right over here. So let's do this finally. So N2 is equal to, what is NH3 in this situation? It is 0.000318 squared. And divide that by H2 squared. H2, we say that is, or cube anyway, 375. We're going to cube that, and then we're multiplying that by 8.8 times 10 to the negative 5th. Alright, however you can fit that into your calculator, do so. And I'm going to write the result down here. I'm going to plug all of that into my calculator, and the result, the final concentration, is going to be 21.8 moles per liter, molar. Remember, all of these are the same concentration as molar. The book just kind of left them out to save space, I believe, but all these concentrations are in molar, except for KEQ, because it's just a constant. It's just a number. All right, that's it for that.